Hello again. Okay, we'll come back and now start our first lecture. Okay, which is a folder based on the link here. Okay, there'll be around 9 to 10 file. Okay, there'll be some additional file later. This one already 11 file. Okay, 1, 2, 3, 4, 5, 6, 11 file here. Okay. Uh, Actually, I did summarize it in a PowerPoint content here. Okay, there'll be only three main results that we will use to apply for our very first homework. Okay, and also this is the link. Okay, the first link is for the content of the lecture one, and the second link is the content for the whole for the every folder for every lecture. Okay, uh, let's go ahead and get started with the idea, okay, of what we will cover here. Okay, and we go to the detail and come back to link with the content. Okay, we will start with the very first slide of what we call the two-stage linear programming model based on the Danzig's paper way back in 1955. Okay, so we come back here. Okay, and let's take a look at the paper of Danzig's. Okay, we're gonna go. I'm not gonna read this paper for you, but to make it a little bit more classic, so we go back in time. Okay, to see. You might see it look very poor quality of printing and everything, but you have to understand that it is this paper, the content is what matter, and it stand over time and make a influence for later research work that still keep going on until today. Okay, first of all, okay, you might look at the pattern of how to write this paper. Okay, the Danzig wrote this paper in 1955. He started with the summary part. Oh, you might look at it, maybe this is like an abstract part of the paper nowadays. But if you keep going, look at that. This is a summary, and you will see that where will this summary end? Okay, and it keep going on, going on, going on until the end of the paper, and you get the reference here. Okay, you have to understand that, and there's only 6 reference here. Okay, and when you look through the paper, you will see that so many mathematical notation. Will I be able to understand the content of the paper? And many of the content here refer way back in the 1955 period. And that time, the world is much different than today's world. Okay, but something when you did something good, it stand through time. Okay, and this paper is one of them. I think that in the year 2005, if you be able to access to the database of the library, okay, you might take a look at the Journal of Management Science celebrating 50 years. And there will be a supplemental part for the last issue of that year. It's a monthly journal, so it's issue number 12, okay, on the year 2005, okay, to celebrate their 50th anniversary. Okay, the editor at that time called many experts, okay, and choose. At that time, they chose the 10 most influential paper. Okay, and the very first paper that was chosen at that time is this paper. It's this paper. Okay, and they reprint it in a much better quality. But actually, I can take that copy and give it to you. But I look in the different point of view that sometimes you just like when you listen to a song. Okay, the artist, the original artist is always the one that you want to go back and listen to. so as the classical paper also. This is where it all started. Okay, Danzig started in 1955. Okay, you have to remember that historically, this is 8 years. Okay, you minus 8, it will be 1947. 1947 is the year that the simplex method created by George B. Danzig was formally announced. The successful, okay, theoretically, okay, that you can solve the general linear programming problem. Okay, and along that time, okay, there will be very important innovation happened in the world way back around in 1950, which was the first computer was built. Okay, so the story goes like it was the right time, right place, right moment. Okay, that linear programming can be successfully using the simplex method, but not solve it, not using by just hand calculation, but it can be programmed. That's how they set up the term called the linear programming. Okay, actually what we're trying to solve in the world of mathematics is we're trying to find the minimization or maximization of a linear multivariate function. Okay, and based it on with respect to a set of constraints modeling as a set of linear inequalities or linear equation. Okay, and those type of activity, okay, was summarized in just one term we call the linear programming problem. Okay, and George Danzig create a method which we call the simplex method, and the simplex method is capable of setting up as a computer program at that time. Okay, and so you can solve it using the computers. Okay, and that's what I told you, that it was this, historically it was the right time, right place, right moment. Okay, but originally way back, the problem in terms of formulation or model of linear programming was created way back a long time ago, even before 1947. But the method was formally announced in 1947. So of all formulated problem in the past was successfully solved within those 8 years before 1955. Okay, and certainly at the start using hand, and then computer come, they use the computers to solve it. And you, as time passed for 8 years, okay, the people who use linear programming and solving by the simplex method start to realize the limitation and the problem of solving many type of linear programming problem. That in the real world, that there was some data that you cannot be confirmed that the is certainty. Okay, but the original linear programming, you required that there was some parameter that you need to solve. Before solving it, you need to know exactly their values. Okay, now we can go back to the original form of what the here what we call the two-stage linear programming model. Originally, if you go back here, okay, you can cut out the variable all parameter related to the vector u and v. The original linear programming have no u or v. Okay, you can formulate most of the problem as minimize c equal to c transpose x subject to a times x equal to b, and x have to be greater or equal to than 0. No u or v. Okay, U of V come later after you reading this paper in 1955 when you add some uncertain parameter here. Okay, but in realities, okay, without U of V variable, okay, we have to know exactly what is the real number within the C vector and the real number within the A vectors and also the real number within the B vectors in order to find the optimum solution of X, okay, using the simplex method. Okay, and so we need to know C, A, and B here. But Danzig's paper in 1955 say that suppose that you don't really know the exact value of C or B or A. Okay, all of this can be uncertain. How do you represent uncertainties? Okay, as we have to go back to the probability model. Okay, you have to know that when you have something that's uncertain, it means that its value can have alternative. Can be, for example, one of the element in B can be between 10 to 20. So the question is, how many alternatives for a value between 10 to 20? And also it depends on how you classify the nature of the alternative. Suppose that you say that, okay, one of the right hand side can be between 10 to 20 and it must be integer value. So this is, you have a finite number of alternatives, right? So we start with 10, 11, 12, 13, 14, 15 to 20. Okay? But suppose that you say, okay, it can be any value between 10 to 20. So now you have infinite number of alternatives, right? Because or in other term of mathematics, we call the first case as a discrete case. Okay, you have a finite number of alternatives, discrete case. The second case we call the continuous case, when you have an infinite number of alternatives. Okay, and remember that we talk about this in only one parameter. I say that one of the right hand side. Suppose you have a lot of right hand side and also the data within A, the data within C. Okay, suppose each of these parameters have their own uncertain value representing by a number of alternatives, which can be finite or infinite. So therefore, when you make a decision X here, okay, you don't really know that whether your A times X can be fulfill the equation of the equality sign here in all alternatives. Okay, this is for example that when you have uncertain value in A or B. It's even worse if you have uncertain for X also. Okay, when you make a decision of X, you don't really know that what is the real alternative of C can appear in realities. But this one in terms of planning in advance. Okay, so you have to consider all possible alternatives. For each alternative, okay, there are some risks that you cannot fulfill the equality sign here, which means that once you make a decision of X under an alternative of A, because each element in A have some uncertainties. So once you make decision X, some alternative you might get A times X equal to B, but since X is constant for all alternatives, in other alternative A times X might not be equal to B. It's either greater or less. That's why you have this variable of U and V with additional here. U plus U and minus V is using to balance, okay, it's using to balance the risky condition of A times X might not be equal to B in all alternatives once a decision making of X was made. Okay, this is only the uncertain between A and B. If you add another uncertain of C, it's even more difficult because X can make only one decision. Okay, once you make a decision, you might end up having several C value here, and that will end up you have multi-objective value, which means that C here, okay, or Z here can have so many alternatives also. Okay, and that would make it very difficult to transform this problem and still maintain what the nature of linear programming is. Okay, and that's the real direction of this what we call the Danzig's paper here. Okay, Danzig's paper here, the whole content, okay, in terms of modeling, try to lead you to this general form of what we call the two-stage. How come we call the two-stage here? Okay, the first stage of this model dealing with X, which is a certain case. Once you make a decision of X, okay, with the uncertain parameter of C, A, or B, you have a risky condition that you cannot maintain A times X equal to B in all alternatives. And also the objective function is not only one C here because C have so many alternatives. Okay, so the addition of U and V here try to, okay, still maintain the linear programming nature here and also balance, okay, the scenario or alternative that A times X cannot equal to B. Okay, and you might take a look at, can U or V be like a slack or surplus variable based on what you study linear programming in the past? The problem is that no, because the slack and surplus variable, you don't really have a cost coefficients here. We call cost coefficients here because we set the objective function as a minimization. Okay, you plus U is look like a slack variable, minus V look like a surplus variable, but they have additional cost here. In reality, how come this additional, where is this additional cost come? Okay, it come with the explanation that once your A times X cannot be equal to B, okay, you need to make a corrective action by either adding U or minus V to achieve the equality sign here. And with this U and V as a corrective action here, there will be some additional cost here. And the additional cost here is not happen to all possible U and V value. Because U and V happen in only one scenario of A. And there will be different U and V for another scenario of A and B. Okay? So the cost here is not the accumulated cost for all scenarios. Because in reality, there can happen only one scenario, the expected one. Okay, so the cost coefficient here that multiplied it to vector U or vector V here have to be what we call the expected cost, okay, for just one scenario, expected for one scenario if happen. Okay, so in other words, it's a average. Okay, it's an average cost rather than the accumulated cost for all possible combination. Okay, and also it depends on the distribution of uncertainty of A and B here also. Okay, you can see that just this one slide tells you a lot. Okay, but where is this idea come from? It's come from here, the content of the paper here. Okay, first of all, Danzig go back and try. Okay, let's start with reading his very first paragraph here. Okay, Okay. Start with the first one. They said the essential character of a general model under consideration is that activities are divided on two or more stages. The quantity of activities in the first stage are the only one that are required to be determined. Those in the second ladder stage cannot be determined in advance, since they depend on the earlier stage, and the random and uncertain demand can occur on or before the ladder stage. Okay, this is a key statement, okay, for the whole paper here. Okay, let's go back to look at the two-stage linear programming model that we have here. Okay, as I told you before, the original linear programming doesn't have the u and v variable. Okay, if I only c transpose x, a times x equal b, and x greater than or equal to 0, the original LP, under the certain parameter of a and value of a, b, and c, you need to find x in order to minimize the c function. There's no u and v here. But with the uncertain condition of a and b and c, okay, leading to the problem of that, in terms of constraint, okay, there will be risk condition that a times x cannot be equal to b in all possible scenarios once x have made the decision. So u and v is added to balance the equation. And also the objective function, there's not one unique objective function because of the uncertain of c. And with this model, we didn't take care of that multiple objective function here. Okay. So with this model, we only look at the uncertainty of a and b. Okay. Suppose c have uncertain condition also. We can transform and move this, let's say, we can move this uncertain objective of c transpose x to the constraint, okay, and did a similar formulation as the original constraint, okay, and add the original objective function to try to make it only single objective function. Okay, that may be a little bit difficult to understand in this stage, but we will show you the example in the latter lecture. Okay, let's look at this only. Okay, so what Danzig say in the first paper is that in the first stage, okay, a certain condition need to be determined, which is x. We define x, but with the decision of x, okay, the second stage is the circumstance of the uncertain condition of b and a, okay, that lead you to an additional variable of u or v. Okay, try to balance of identify the corrective or opportunistic cost, additional cost, when a times x is not equal to b in some scenario based on the uncertain of a and b. Okay, with this additional u or v, you can add this as the expected cost is an uncertain cost, okay, add up with the deterministic cost of c transpose x. And that's the resulting formulation of what we call the two-stage. The first stage is the original LP. The second stage is with uncertainty of the first stage parameter, leading to, okay, the risky condition that the constraint cannot be satisfied in all scenarios. So with the risky condition like that, the u and v come to help to balance and still maintain what we call the structure of linear programming. Okay, so now we go back to the paper again. Okay, I'm not going to read all of this, but you can, it's a historical moment, okay, for this type of problem. We're going to go to some only main content here. Danzig say here that initial work of this paper was stimulated by discussion with A. Ferguson. Okay, so this is he just wrote what he did. Okay, that I wrote this paper because I discussed this with Professor Ferguson. Okay, who proposed that linear programming be extended to include the case of uncertain demand. but that's the application for the carrier fee to airline route, whatever. And the demand uncertainty can be modeled as a probability distribution. Okay, but the example that Danzig gives is he trying to go back to the very basic problem we call the diet problem, minimum expected diet problem here. Okay, and the second example that he used is for the shipment for the transportation problem. Okay, I'm gonna finish this second clip, okay, by introducing you that, okay, one of the early application of linear programming success under certain conditions is the minimum cost diet problem, which was originally proposed by the Nobel Prize agriculture economist, okay, George Sticker, okay, way back before 1947, before the Simplex Method was created. Okay, and the second paper, okay, is that lead to the second example is the problem of transportation problem under uncertain demand. Okay, so Danzig used these two examples to give you the idea how his resulting work would appear to you. Okay, and we'll show you and give you a specific explanation in the next clip. Okay, so for this clip, okay, what you, in summary, you should understand, okay, this is a resulting of paper, Danzig's paper here. Okay, we call the two-stage linear programming model here. Okay, and this is a class of the problem that leading to a large-scale linear programming problem. Okay, and we'll show you in the next clip that how this resulting model become a large-scale problem and giving you an example. Okay, so for at this moment, I'm going to stop you with this clip. Okay, you might review the clip by re-listening and re-watching it again. Okay, and see you in the next clip.